Hello, welcome to Singapore Math Live Solutions Recording. This is the very first week and the very first recording for the Primary Math 5 class, and I'm going to work first in the challenging word problems, page 3 through 6 on whole numbers. These are the ones that are assigned for your student to do sometime during the first week of class. And I will tell you that the whole numbers section is kind of about number theory. There's a lot about thinking about math with that, and it's not so much computation, it's more theory-based than computation-based. And so that means that we're going to have to put our thinking caps on and really work hard on it. Some of them are really easy, and some of them will take a lot of thinking and systematic working and things like that. So let me jump right in and work these with you. You'll notice each time when I'm working a problem, I'll put the number at the top left of the screen. And so if you already know how to do number 1, but you really want me to see how I worked number 10, you can use your fast forward button and get all the way over to chapter 10 or number 10 and see how to do that. So here we go. Number 1 talks about Mr. Lee, who has 100 stickers, and he has 6 people he's given them to. I'm going to abbreviate the names. We have A, C, E, G, I, and K, and all of these kiddos get some stickers from Mr. Lee. He has 100 stickers to give away, and the question is, who gets the last one? Well, if you think about what it means to divide, very simply we're going to say we're going to take these 100 stickers and divide them into 6 groups. And so you can do that on the side, you can divide that, and what you're going to come up with is that there are 16 with a remainder of 4 stickers left. Now what that means, sometimes we don't think about what division means. It means I'm going to give everybody a sticker, and I'm going to give everybody another sticker, and I have enough to do that 16 times. Everybody's going to have 16 stickers all the way start to finish. I have 16 groups of 6 stickers, and then I have 4 left over. So that 4th sticker, the very last sticker, is going to go to Jenny. Lucky Jenny. She's going to get the 4th sticker after all rotations have been gone through. Now this would be kind of considered a remainder theorem problem, and remainder theorem is something I see a lot even on SAT tests. And so interestingly enough, learning about the number theory in these problems is really helpful. For number 2, I'm going to pause the recording and make a drawing. The miracle of recordings, I can pause and draw all this out without having you sit and painfully watch me as I write it. But here's what this question is asking. And this question, by the way, really cannot be done without a systematic list. And so sometimes, and this is a problem that I would call a discovery kind of a problem, but we have to come up with a systematic list to solve it. When I read this, I have no idea how I'm supposed to figure this out. The only thing I can do is start with something that I know and look for a pattern. There are always patterns with numbers. That's a really cool thing about math, is that there are patterns all over the place. So if you're looking for a pattern, what I need is a 2-digit number. So I start with the first 2-digit number. That would be 10. And I want to find a 2-digit number that is 3 times the sum of its digits. So here is my list of 2-digit numbers. Now notice I've not made all the 2-digit numbers because clearly I can go all the way to 99, but this is the number that is 3 times the sum of the digits. And I went until I figured out that I had some sort of a pattern that's beneficial. Notice I'm looking for the time when the number is the same thing as 3 times the sum of the digits. That's what it's asking me. Well, first off, notice that 3 times the sum of the digits are multiples of 3. When I see it, it makes sense. Oh yeah, maybe I should have even known that. If I take 3 times the sum, I'm going to get a multiple of 3 from 3 to 30. Notice after 30, the number goes back, and it goes from 30 back to 6 again. So the only numbers, see, I found a pattern, and I've just realized that if the number itself is going to be the same thing as 3 times the sum, then my only options are these numbers. I must have, there we go, sorry. All right, there we go. I must have the numbers either could be 12, 15, 18, 21, 24, 27, or 30. And remember, I want my number and 3 times the sum of the number to be the same thing. So I'm going to make a new list with just these options. These are the only options I have, because 3 times the sum of a number is going to be limited to these options. Okay, so the sum of 1 and 2 is 3, and if I multiply it by 3, I do not get 12. The sum of 1 and 5 is 6. If I multiply it by 3, I don't get 18. This sum is 9. 9 times 3 is 27. The sum of 2 and 1 is 3. Multiply by 3, I don't get 21. This is 6. Multiply by 3, I don't get 24. And finally, the sum is of 2 and 7 is 9. If I multiply it by 3, I do get 27. So through my discovery method, through having a systematic list and a systematic way to work through my data and finding a pattern, I've discovered that 27 is that number. 27, a little room to write here, 27 is a 2-digit number. 3 times the sum of those digits is the digit itself, the number itself. And that's what I was looking for. All of that can be done, really the only way I know to do it is to set up a chart and come up with a discovery. So number 2 is going to be a pretty time-consuming problem. And if it took you a long time, it did me too. Number 3. Lewis has a set of CDs. He's going to put them in stacks. When he arranges them in stacks of 2 and 3 and 5, he has a remainder of 1 each time. That means there's 1 left over. Okay? He can't put it in a stack because there's an extra one after all. And so the question is, what is the least possible number of CDs that he can have? How many CDs does he have? That's what we're trying to figure out. Okay? And what we need to realize is this. There's a number that 2 and 3 and 5 will go into evenly. And if I add 1 to that, then each of these will have a remainder of 1. Right? So what is a common multiple of 2 and 3 and 5? Since 2, 3, and 5 don't have any common factors, I just multiply those together and I come up with 30. And so 30 is the number that I can put 30 in stacks of 2, I can put 30 in stacks of 3, I can put 30 in stacks of 5. All of those work out evenly. So my CDs, I must have 31 CDs. Because if I have 31 CDs and I put them in stacks of 2, I have 15 stacks plus 1 extra CD. If I have 31 CDs and I put them in stacks of 3, I'm going to have 10 stacks and 1 extra. And if I have 31 CDs and I put them in stacks of 5, I only have 10 stacks, but I still have 1 extra CD. So that is what they're asking, and the idea of understanding about remainders. If you have a remainder of 1, that means you find where you go in evenly and you go up 1 more. Again, I would call that remainder theorem, all right? And that is a skill I see in upper math. Remainder theory, the theory about remainders, is something you see in upper math, SAT tests, things like that. It happens frequently. So that's a great one to really understand. Number 4 is a logic problem. You've got a textbook. It's labeled from 1 to 100. We want to know how many pages it contains the digit 2 but is not divisible by 2. Now, when you see the phrase divisible by 2, please have in your mind the idea that that's a nickname for another word you're very familiar with. Do you know what word that is? If a number is divisible by 2, it is an even number. So if it's not divisible by 2, it's not even, or we call those numbers odd. It's an odd number, and yet it contains the digit 2. Well, anytime you have a number, and we have from 1 to 100, so we're limited from 1 to 100. Anytime you have a number with a 2 in it, like for example 32, that's an even number. If the last digit is 2, then it's an even number. So none of those numbers would work. You could think about the number 2 and 12, 22 and 32, all the way up to 92. None of those numbers will work because they're all even numbers. Remember, I want to find one that is not divisible by 2. So it must be that the 2 would be in the tens digit instead of in the ones digit. So then I have the 20s. But wait a minute, I don't have the 20s because 20 is even. That means it's divisible by 2. So is 22, and so is 24. So finally I come to the end of my logic and say, okay, the numbers that meet my criteria are 21, 23, 25, 27, 29. They're the odd numbers in the 20s because they have a digit 2 in them, but they're not divisible by 2. So the answer is 5, and those are the numbers that are there. Number 5 is a very interesting problem. If you don't already know the answer, I think you'll be surprised by it. A jigsaw puzzle has 50 pieces. Now, it would be very simple to take 50 pieces of a puzzle and put it on your table and have your child try this out for themselves because they may not believe you. Okay, and so you don't have to match them. You could tell them just to pretend. If they just put 2 pieces together, just pretend like they go together and see how it works. Okay, so we have 50 pieces, and I'm going to take on my table, I'm going to put 25 on the left and 25 on the right, and I'm going to join those. And again, just don't worry about making the puzzle fit. You can if you want to, but don't worry about making them fit. If these 25 pieces, each one of these connects with each one of these, then I'm starting with 50 individual pieces, and now I'm coming down to 25 groups. Right now we have groups of 2 because there's 2 in each one. Okay, and I have made 25 moves. Now the problem itself defines a move by saying joining 2 pieces or 2 groups is one move. So I have 25 individuals on one side of the table and 25 individual pieces on the other side. I put each one of those with one pair, and that makes 25 moves. And now I have 25 groups. They happen to have 2 pieces per group. Okay, now I can't divide those evenly on my table, but I'm just going to stick 13 on one side of the table and 12 on the other. It's going to be an odd number, but that's okay. I can put together 12 of those. Okay, so that's going to be 12 moves. And when I'm through, I'm going to have 13 groups. Right? 12 of these matched with 12 of those, so now I have 12 groups. And that one extra one just kind of has to come on down and hang out with the rest of them. Let me transfer to the top of my next page. I have 13 groups now, and I'm going to separate on my table. I put 7 groups on one side, 6 groups on the other. When I put those together, I'm going to have 6 moves, and it's going to result in 7 groups. Okay, now this is a great one to make concrete. Always, when you can, make it concrete. Take out 50 anythings and put them in pairs, or even just start with 7 and show your kid how it works with 7, and then they can extrapolate back and understand how it works with 50. But again, I'm going to put 4 on one side of my table and 3 on the other side of the table. Now each of these groups has several pieces in it. When I join them, I can join 3 and 3, and that will be 3 moves. and I'm going to have 4 groups. And then, it won't surprise you now, you've seen the pattern, I'm just going to keep on going to the end. I have 2 on each side of the table, and I'm going to go join those together, and that will give me 2 groups, and it will cost me 2 moves. Basically, I'm out of space here, but these 2 groups can be joined together, and that's 1 more move that completes my puzzle. Alright, so I did 25 moves, and then I had 12 moves, and 6, and 3, and 2, and 1. And if you count the moves that you made, you may be surprised to find out that it's going to take me 49 moves to work the puzzle. See, it seems to us that if you have 50 pieces and you can join them in groups, that I will be cutting down on the number of joins that I have to make. But the truth is, if you just put 1 on at a time, you get 49 moves. And if you put them in as big of a group as you possibly can, you have 49 moves. That's worth pondering. Very interesting result. Problem number 6. We have a dartboard, and our person, Jill, made 100 points. And the question is, how many darts did she throw? Asking 2 questions here. How many darts to score 100 points? And the second question we're asking is, where did they land? Okay, so the back of the book has 1 answer. There are at least 2. I've only found 2. I think there's only 2. But let's talk about that. The idea here, when you're thinking about it, what you have to realize is you've got to somehow make the numbers into tens. Because to get to 100, you've got to be counting, you've got to get to a 10 somehow. And so when I look at it and saw it, I realized that a 12 and a 23-point dart will give me 35 points. And if I happen to be able to throw a 12 and a 23-point dart twice, then I would be up to a score of 70 points. And conveniently enough, there's a 30-point spot on the board, and that would give me 100 points. And I would have thrown 5 darts to get there. So how many darts? This answer would be 5. And where did they land? I had 2 land on 12, 2 land on 23, and 1 land on 30. And that is an answer choice that works. However, I could also solve it by making tens if I used 12 and 12 and 19. Notice that 12 and 12 and 19 add up to be 50. Clearly, 2 50s is going to make a 100-point dart game. So in this case, I had to throw 6 darts, and I had to throw 4 12s and 2 19s. So the answer to the question, how many darts, basically depends on how good of a dart player you are, right? I would be in the orange category, throwing them on the outside boundary. If you're a good dart player, maybe you could be on the green category and throw a 30-point bullseye along with the rest of them. But one of those ways, either of those ways, would get you 100 points. One of them would use 5 darts, and one would use 6 darts. Number 7 talks about tennis players in a tournament. Anytime you can, take a concrete or take an abstract concept and make it into as concrete of a problem as you can. And so, for example, I have 7, sorry, there's 6 players, so let me erase one of those. Only need 6 players. Here's my 6 players. I'm just going to call them player A, B, C, D, E, and F. And remember, we want to make it as simple as possible. So we don't have to worry about everybody playing fairly at first or playing the same amount of games. Maybe player A plays all of his games and then he goes home. And so player A plays a game with player B and with C, D, E, and F. And then player A is finished with the tournament play. He's through. And then player B says, now it's my turn. So player B, of course he's already played with player A, Player B is now going to play with everybody that's left in the tournament, and he has 4 games. Player C now has his turn to play with everybody. Now, it's not very efficient if you're a tennis player because you wouldn't want to play all of your games back to back to back, but we're not worried about efficient tennis playing. We're just trying to organize our data in a way that we can solve the problem. So by now, you see the pattern, right? D is going to have to play 2 more games. E has to play 1 game, and by the time it gets down to player F, he's already finished his games. He's played with everybody else all along the road. And so how many games are going to be in this tournament? 5 plus 4 plus 3 plus 2 plus 1 is a total of 15 games. Organizing your data into a way that you can easily solve it is a huge part of solving math well. Number 8. We have 10 numbers that if you add them together, all of those numbers added together is going to give us 2,783. Now, one of the numbers used to be 397. And all the numbers are the same. One of the 10 numbers is changed to 502. So the question they want us to find is, what is our new sum? Well, remember, all of these other numbers are the same. Now, mathematicians are extremely particular with our numbers. And so when they say one number changes, then you can know that the rest of the numbers didn't change, or we would have had to say so. When you change from 397 to 502, you have gone up 105. Now let me pause a second and talk to you about this. Singapore Math likes us to do mental math. I like us to do mental math. If we go from 397 to 502, you could subtract that. You could also think, I need 3 more to get up to 400. From 400 to 500 is a difference of 100. And then I need 2 more to get to 502. So without making a big deal out of it, I can mentally go from 397 to 502 by realizing that I have these 3 separate jumps, which total 105. If all the numbers are the same and one number jumps 105, then my total is going to jump 105 as well, and the sum of the 10 numbers is going to be 2,888. Numbers 9 through 11 are really the same skill, the same math skill. And so I'm going to work each one of them, but just so you know, if you're watching the recording, I put that up there so we can show you all of the same idea, the same strategy is going to work for all of these. I'm going to pause a second and give you a picture. All right, I went ahead and drew out what it said to us, and I'll walk you through it. It tells us in bag P there's 12 toys, and in bag Q there's 66, so I showed that in blue. And then we have that we are given, Mrs. Murray added the same number of toys to each bag. So I put a purple square at the end of each bag, and that represents the number of toys that Mrs. Murray added. Now after that, I'm told that bag Q has 3 times as many toys as bag P. On the right side of the page, I drew a picture to help us understand what it talks about. Very simple, very obvious, but sometimes we have to think about it to make sure we really understand it. If Q has 3 times as many as P, then that means P has 1 group and Q has 3 groups. Okay? Now, here's what I know about these. According to this, this is 1 group, just like we said, and this is 3 groups. Now, I know one of these groups is 12 plus a purple block. So I could mark it off right here and say, if this is 12 plus a purple block, that's one of those groups. And so if 12 plus a purple block is 1 group, then I used to have 66. Matter of fact, I should write this up here. This whole thing up to my purple block, before Mrs. Murray added it, I had 66. But I've divided that now, and I have 12 there, so I must have 54 over here. But what I know is that 54 is the same thing as 2 groups, because remember, I have 3 pink groups. Now sometimes it gets hard to draw it all and keep us really steady, but remember, I have 3 groups that are the same as one of these. Now my drawing doesn't look, it's not perfect and it is not proportional, okay, but we want to understand abstract things, we want to be able to do it. So this is one group and this is 3 groups, and 12 plus a purple box is equal to 1 group. So these 54, if I divide that into 2 even groups, must be 27. So each group, and remember, I have 1 group in pink, I have 3 groups in, 1 group in P, 3 groups in Q. Each of my groups is 27, and each of my groups is equal to 12 plus that purple box that we have, and each of those is equal to 27. Inside that box, I must have 15 toys in order for 12 plus the box to be 27. Now, it'll take a few more of those possibly to get really good at doing them, but that's the idea for each one. And I would love for you to get your students used to checking their work and making sure that they have the right answer. So what we're saying is that person P, bag P, started out with 12 toys, and bag Q started out with 66 toys. And then we're saying that the amount Mrs. Murray added was 15 for each one. That would give you 27 for bag P. That would give you 81 for bag Q. And the question is, does bag Q have 3 times as many toys as bag P? And the answer is yes, it does. So we've done the problem correctly, and we found that, I didn't write my answer anywhere, 15 toys were added. All right, now let's look at number 10. Same strategy. All right, again, I drew the drawing for us. Joseph has 28 magnets. Sarah has 157 magnets. Always helps to make sure you label it correctly. It's 157 magnets. After each of them added the same number of magnets to their collection, in this case I used a green box, Sarah has 4 times as many magnets as Joseph. And so Joseph has 1 group and Sarah has 4 groups. And we want to know how many magnets each of them added to their collection. Now that we've done it once, I hope it makes sense to do the same thing again. If I take Sarah's magnets and I subtract 1 group, I know 1 group is made up of 28 and a green box. So if I take the 157, keep my color coding separate in case that helps you to see what I'm doing, I have 157 plus a green box, right? Now let me just do it this way. I'm just going to draw a line here and say that this is 28 and a green box. So this is 1 group. Now that means that if I have 4 groups, I must have 3 groups left over here. This is 1 group, this is 1 group, and this is 1 group. Okay. How many do I have left over here? Well, I have 157 minus 28. 157 minus 28 is 129. I know that 129 is equal to 3 groups. Remember, I started out with Sarah having 4 groups, and I know that each group is 28 in a green box. So when we got rid of 28 in a green box, instead of having 157, now I have 129, and I know that that's equal to 3 groups. So if 129 is equal to 3 groups, Then I'm going to do 129 divided by 3, and I find out that there is 43 in each group. Remember, each group, just like Joseph is his name, each group is comprised of 28 and a green box. And I know that each group has 43. Well, if each group is 28 and 28 and a green box, and that makes 43, then in this case also, happens to be the same answer as the last problem, I must have added 15 magnets to each one. Again, extremely good habit to check your work and find out. If Joseph had 28 and Sally had 157, if they each added 15, then Joseph has 43 and Sarah has 172. And the question is, if I take Joseph's 43 and I multiply it times 4, does he end up with 4 times the amount, or does she end up with 4 times Joseph's amount? And that is, yes, Joseph's amount times 4 gives me Sarah's amount, and that means I know that my answer is correct. Help your students get in the habit of checking their work on a regular basis, when possible. Number 11, exact same idea. Olivia has 32 stamps. We're told that Sally has 154 stamps. Each of them buy the same number of stamps, and at the end of it, Sally has 3 groups to Olivia's 1 group. Okay, now, hopefully by now, 3rd time in a row we've had this similar kind of problem. If 1 group is 32 plus a green box, then I could cut off 32 of these, and this is 1 group, and what's left will be 2 groups. When I have the 154 and I take off the 32, then what I have left over here is 122, and those 122 comprise 2 groups. So 122 divided by 2 tells me that each group must have 61 in it. So back to my original picture, 1 group is made up of 32 and an orange box, and that's equal to 61, which tells me that I must have 29 added in my orange box, because 32 and 29 gives me 61. So 29 is the number of stamps that they each purchased. You got to be careful about these mathematicians. We always are picky about our words. How many stamps did they buy in all? We just found that each of them purchased 29, so 29 times 2 is 58 purchased in all. Really good idea to teach your students to read the questions carefully and make sure they answer exactly what is asked, because that's the way they're going to not make a mistake. Again, please go back and check your work. Make sure that you have the right answer. If we have 32, if Olivia has 32 and she adds 29, then she has 61 stamps. Sally had 154. She purchased the same number, 29, and that gives her 183 stamps. And we're hoping that Olivia's times 3 gives us Sally's, and in fact it does. That tells me that I've done the problems correctly. All right, that is the end of the word problems for whole numbers, part 1.